In this video, we are going to talk about two more optimization examples. And so these are a bit more complicated than the ones we did previously. So the first one is a woman launches her boat from point A on a bank of a straight river that is 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank. She can row her boat at 6 kilometers per hour and run at 8 kilometers per hour. We want to find where on the opposite bank she should land her boat to reach point B as quickly as possible. Okay, so let's actually draw a picture of this situation. So we've got this river here that is a distance of 3 kilometers wide. We've got some point A here on this side and some point B here on the opposite side. And then she wants to go from point A to point B. And then if we think of going straight across, just call this point C, the distance here from point C to point B is going to be 8 kilometers. And so that's the 8 kilometers downstream. And so what we're doing is we've got that we're rowing some distance to some point D here, and then running the rest of the way to B. So we're going to row across to some point D, and then run the rest of the way to B. And we want to figure out where she should land, so how far downriver she should land, in order to get to point B as quickly as possible. Okay? And so hopefully that makes sense. So what we're going to do here is we're going to let x be the distance that she goes downstream. So it's going to be the distance here from C to D. And so the distance from D to B is going to be 8 minus x. Okay, so x is how much downstream she goes in this process of rowing. And so we want to figure out how far she's going distance-wise in each case. And so here we have that she's running 8 minus x. And we want to figure out how far is she rowing. Well, she's rowing this distance right here, which I'll write as d for a second. And so we know this is 3 and this leg is x, and so d is just going to be the square root of x squared plus 9, which is 3 squared. So the running distance is going to be 8 minus x. The rowing distance is the square root of x squared plus 9. And we want to minimize time, because that's minimizing how long it takes her. So we want to minimize travel time. Okay, so that is the idea. And so what we know right now is we've just figured out the distances. We also know the rates, so I will write those down. So the running rate is 8 kilometers per hour, and the going rate is 6 kilometers per hour. Okay, and so we want to figure out time. Well, we know that the rate that you move at is equal to your distance divided by time. And so solving for time in this equation, we get time equals distance divided by the rate. And so to figure out the rowing and running time, we have the rowing time is going to be the distance she rows, which is the square root of x squared plus 9, divided by how fast she goes, which is 6. And then the running time is equal to 8 minus x divided by 8. The running distance of 8 minus x divided by the running time of 8. And so this then gives us our time then. The total time. It's just going to be the sum of these two. So it's going to be 8 minus x over 8 plus the square root of x squared plus 9 over 6. So that's the total time, and this is what we want to minimize. Okay. Now, this took a lot of kind of build up to get to this equation, but remember, we're actually solving a pretty complicated situation of figuring out where to land on the opposite shore to minimize the amount of time. This could be like in a race or something, so she's trying to get from point A, the starting point, to point B, the ending point, as fast as possible. And now we want to consider the domain here to just get a closed interval. And so clearly x is between 0 and 8, because it would not make sense for her to row to some point before C. Rowing straight across is obviously going to be fast. Well, some point diagonally down is going to be faster than going diagonally up. And there's no point in rowing past the point B and then running back. And so running past the point B would be corresponding to x being greater than 8. And so we're bound between 0 and 8. And so now we want to figure out the derivative and set it equal to 0, just like we've done before, to find the minimum. Notice we only have a value of x, that's our only variable, so we don't have to replace variables. So taking the derivative here, I'm just going to call this function t for short. So t prime of x. The derivative of 8 minus x over 8 is just going to be negative 1 over 8, plus then the derivative of the top is going to be 1 over 2 square roots of x squared plus 9 times the derivative of x squared plus 9. And this is all divided by 6. So this gives us negative 1/8 plus, if we multiply this out, we're going to have 1 over 12 square root of x squared plus 9 times 2x, which gives us x over 6 square roots of x squared plus 9 minus 1 over 8. Now the denominator here is clearly never going to be 0, because x squared plus 9 is always greater than or equal to 9. So we just need to figure out when this is 0. So we're going to set x over 6 square roots of x squared plus 9 minus 1 over 8 equals 0. So that means x over 6 square roots of x squared plus 9 must equal to 1/8. Then multiplying both sides by 8, what we're going to get is 8x over 6 square roots of x squared plus 9 is equal to 1. It tells us that 8x equals 6 square roots of x squared plus 9. So 4x is going to be equal to 3 square roots of x squared plus 9. Squaring both sides, we get 16x squared equals 9 times x squared plus 9. And so multiplying this out, you get 16x squared equals 9x squared plus 81. So 7x squared is equal to 81. X squared equals 81 over 7. And so x is then going to be equal to the square root of 81 over 7, which is 9 over the square root of 7. Okay, so we got 9 over the square root of 7. So this is our critical point. Now, using the closed interval method, we're going to compute the time at each of the endpoints as well as the midpoint. And so we have t of 0, t of 9 over the square root of 7, and t of 8. Now, just as I remember what t looks like, I'm just going to write down the values of these things, or approximations. But remember that t of x is equal to the equation, the square root of x squared plus 9 over 6 plus 8 minus x over 8. So that's what I'm plugging these into. I'm just plugged them into a calculator, though. So if you plug in 0, you get out 1.5. If you plug in 9 divided by the square root of 7, you get about 1.33. If you plug in 8, you get about 1.42. And so our minimum does happen at this 9 over the square root of 7. And so the smallest value goes at 9 over the square root of 7. And so the woman should land at a point 9 divided by the square root of 7 kilometers, which is about 3.4 kilometers downstream. Okay, so that is how far downstream she should go. Meaning that if we actually look at that picture again, with A here, the point D that she should land at is a point where this distance here is about 3.4 kilometers downstream. And then B's over here. And so she should land over at D and then run down to B from there. Okay? And so that was a more complicated optimization problem. But the point here that we're really trying to get across is that we can solve somewhat complicated situations of figuring out how to minimize time, maximize various things, using these ideas of derivatives. Okay? And so the next thing we want to do is the following example. And so we want to find the area of the largest rectangle that can be inscribed in a semicircle of radius r. Okay, so we want to find the largest possible rectangle that we can inscribe in a semicircle. And so the way to visualize this is if we actually draw a semicircle on the coordinate plane of radius r. We'll just draw the upper half of one. So we've got this semicircle, and then we're inscribing a rectangle inside of it. So that means we're putting some rectangle inside of it, and we want to figure out what is the largest area for such a rectangle. Okay, and so if we actually picture this as being the points where it touches is the point x comma y, then our vertical distance will be y, and this distance here is going to be x. But because of symmetry, this distance over here also should be x. And so the total length of the rectangle is going to be 2x, and its height is y. Okay? And so from this, then, we have the area for the rectangle is equal to 2x times y, where x and y are literally just the coordinates on this semicircle that we have drawn. And now to eliminate the value of y, we're going to use the fact that it lies on this semicircle. So the equation for a semicircle of radius r, you may remember, is that y equals the square root of r squared minus x squared. And this just comes from the equation x squared plus y squared equals r squared, and solving for y. And so that tells us y equals the square root of r squared minus x squared, so we can replace that in our area equation. So our area then equals 2x times y, but y is the square root of r squared minus x squared. And so this then is our expression that we want to find the minimum of, or maximum of. Now we do have bounds here, so if you think of this picture, the smallest possible value for x would be up here at 0, and the largest possible value would be over here at r. So we've got a closed interval of 0 to r that we're working with. So we're going to use the closed interval method to find where the maximum is at. So we're going to take the derivative. So the derivative of this, using the product rules, the derivative of 2x is 2 times the square root of x squared minus of r squared minus x squared plus 2x times the derivative of the square root of r squared minus x squared, which is 1 over 2 square roots of r squared minus x squared times the derivative of r squared minus x squared. Now remember, we're taking the derivative with respect to x. R is just a constant. So this becomes 2 square root of r squared minus x squared plus 2x times, it's just going to be negative 2x over 2 square root of r squared minus x squared. So this simplifies as 2 square roots of r squared minus x squared minus 2x squared over r squared minus x squared. Now since we are going to figure out when this is 0, I'm going to get a common denominator. So I'm going to multiply the first thing by the square root of r squared minus x squared. So we have 2 times r squared minus x squared divided by the square root of r squared minus x squared minus 2x squared over the square root of r squared minus x squared. And so this then becomes 2r squared minus 4x squared divided by the square root of r squared minus x squared. Okay, and so this then is going to be the thing we want to set equal to 0. So we're finding critical points again. So we set this equal to 0. So we have 0 equals 2r squared minus 4x squared divided by the square root of r squared minus x squared. We don't need to worry about when the denominator is 0. That does happen when x equals r, but remember, that was one of our boundary points. So our boundary was 0 and r. So r will be a critical point as well, but we already were going to count it anyway as a boundary point in the closed interval method. So we really only need to worry about when we get this equality here. That'll happen only if the top is 0. So we have 0 equals 2r squared minus 4x squared. So 4x squared equals 2r squared. So 2x squared equals r squared. Or in other words, we're going to have x squared equals r squared over 2. So x is going to be r over the square root of 2. So that is our other value, is r over the square root of 2. So now we're going to plug those in for the closed interval method. So we want a of 0, a of r over the square root of 2, and a of r. Now if we plug in 0, again, our area formula if you don't remember, our area formula was 2x times the square root of r squared minus x squared. So if we plug in 0 for x, we're going to clearly get out 0 because we have a 2x in front. If we plug r in, the square root of r squared minus x squared is 0, so we get out 0. And if we plug in r over the square root of 2, we get 2r over the square root of 2 times the square root of r squared minus r squared over 2, which equals 2r over the square root of 2 times the square root of r squared over 2, which equals 2 times r over the square root of 2 times r over the square root of 2, which equals just r squared. And so that then tells us that the area for the largest possible rectangle is r squared. So the area of the largest possible rectangle is r squared. Okay, so this is just another example of what we can do with optimization questions. Okay, so hopefully that is helpful just to see a bit more of examples of solving these. The more of them you see, the more into the pattern you get of how to solve these.